Good afternoon, everyone. Thanks for joining us. Welcome to the 2023 NECAN webinar series highlighting monitoring priorities for the Northeast. This is the 5th webinar in this series, and today's theme is OA and modeling. So with the assistance of this series and our presenters, the NECAN Steering Committee will be working on the development of a regional monitoring plan for the Northeast. And these webinars will serve as an informational resource for them as the plan begins to come together. Updates on this series are shared through our mailing list and on our website, so be sure to check those out for the full schedule and registration information. At the conclusion of the presentations today, the steering committee will be asking our panel some questions, and then we'll open it up to a more general Q&A for everybody else. So during that Q&A session, feel free to use the raise hand function to ask a question, or just you can submit a comment or question through the chat box. First up, we'll hear from Wang. Lou is a modeler with expertise in both hydrodynamic and biogeochemical models, focusing on ocean acidification in the Northeast US region. Lou recently completed her doctoral studies in Dr. Changsheng's lab at University of Massachusetts, Dartmouth, and passed her dissertation last week, and will continue working as a postdoc in Dr. Chen's lab. Congratulations, Lou, and go ahead and share your screen.
Okay. Thank you for the introduction. We'll share my screen.
Yeah, you can show your screen. Yeah.
Yeah, okay, can everyone see my screen now?
Yep.
Yeah.
Okay.
Good. You can see very clear.
Okay. So my topic today is the simulating ocean acidification in the Northeast US region using a fully coupled three-dimensional biogeochemistry and ecosystem model. And this work is done under the guidance of Dr. Changsheng Chen and Joe Salisbury. I will introduce. Why I can't? Okay. So, next, I will introduce from the following 4 parts: motivation, objectives, main findings, and summary. First, start with the motivation. So the U.S. Northeast region is the physical condition here is very complicated. It is influenced by the global to basin scale circulation, including the buoyancy-driven coastal current coming from the upstream Labrador Sea, and also the Gulf Stream and Walker and Wang eddies separated from it from the south, and also the clockwise and anti-clockwise circulation in Gulf of Maine and Georges Bank. And the factor influence the ocean acidification condition here can be summarized as the short-term factors and long-term factors. The short-term factors include the primary production, the river flux, and the benthic processes, and also Wang and Wang eddies. And the long-term factors is mainly from the climate change, such as the increased CO2 loading from atmosphere, and also the warming, and also the increased river flux. But the response of ocean to this process may be different. For example, the CO2 loading. This figure shows the pH and PCO2 trend over the last decades in the Mass Bay region and the Northeast US region. We can find the trend of PCO2 is opposite in these 2 regions. The PCO2 is decreasing in Mass Bay, but increasing in the Northeast US region. This means the CO2 loading from the atmosphere may not be the primary mechanism that influence ocean acidification condition in the nearshore area. And both the physical and biogeochemical processes can be influenced by the climate change. So for the physical processes, it can be influenced by the atmospheric forcing. For example, the sea surface temperature and the wind is increasing over the last decades, especially from the period after the 2012. And also it can be influenced from the boundary inputs, mainly from the rivers and the inflow from upstream. For example, this figure shows the river flux in the Northeast region is increasing over the last 20 years. And the Scotland Shelf and Gulf of Maine is region significantly influenced by the water inflow from the upstream with low salinity and low TA. And this inflow may be increased due because of the warming, because of the melting of the ice. And also previous work found that the number of Wang and Wang eddies have increased in the last decade. This will affect the water transport from the slope region to the shelf region. And for the biogeochemical processes, the increased atmospheric CO2 and river flux will enhance the ocean acidification by leading to more CO2 into the ocean. But the primary productivity can also be influenced by all the regions, including the increased atmospheric CO2 and more nutrients from river and higher ocean temperature. So the ocean acidification condition in this region is influenced by the fully interaction from the physical and the biogeochemical processes. So there comes our questions. What is the primary mechanism controlling ocean acidification in different areas of the Northeast Shelf region? And what is the contribution of various physical and biogeochemical processes to ocean acidification variability in our region? And what will the climate change impact the ocean acidification condition in our region in the future? So the observation is insufficient to answer these questions. And also, as I mentioned, the interaction between the complicated physical and biogeochemical processes. So our first objective is to develop and validate a fully 3D prognostic physical and biogeochemical couple model, the Northeast biogeochemistry and ecosystem model. We call it NECAN, and also apply NECAN to simulate the physical and biogeochemical fields over the Northeast US region, and then identify the relative contribution of various physical and biogeochemical processes to the ocean acidification variability in our region, and at last project the impact of climate change on the ocean acidification condition in the future. So our approaches to achieve the objectives can be separated into 3 parts. The first one is model development and the handcast experiments and the projection experiments. Next, I will introduce some details about our approaches. I'm sorry. Okay, I will just continue. So the NECAN is coupled with our NECOF and the European Regional Sea Ecosystem Model, the ESOM. The NECOF will provide the physical forcing, including the wind, the shortwave radiation, and the air pressure, and the ocean current, salinity, and temperature to the ESOM. The ESOM is not only include the lower traffic level food web, but also the carbonate system. So in its planning part is included 4 kinds of phytoplankton, 3 kinds of zooplankton, the bacteria, the organic matters. It also considers the interaction between the atmosphere and the benthic part. The ESOM is already coupled with FVCOM by the Plymouth Marine Laboratory in UK. But to apply ESOM in our region, some additional work need to be done. So we added the volume and mass conservation adjustment to correct the errors due to the time interpolation of the physical input field in the offline model, and also improved the numerical accuracy of biogeochemical tracers advection by applying TVD and MD data schemes, and also implemented the groundwater model to simulate the savage outfall in Mass Bay region, and also replaced the biogeochemical parameters based on the local and regional database. The difference between the biogeochemical model to the hydrodynamic ocean model is that there is plenty of parameters and empirical equations need to be determined, and the parameters is varied from region to region. So we first conducted NECAN into a small region, the Mass Bay region. First, for the 1D experiments, the aims of the 1D experiments is to do the sensitivity study of each parameter and also determine the parameterization suitable for this region, and then test if NECAN can simulate the observed seasonal and interannual cycles of biogeochemical processes. Then we moved to the 3D experiments in Mass Bay for the simulation of 2016, and then to the larger domain, the Northeast US region, to do the simulation of 2017 and 2018. So the aim of the 3D experiments is to simulate the physical and biogeochemical fields over the Mass Bay and Northeast US region, and then identify the relative contribution of various physical and biogeochemical processes to the ocean acidification variability. After the handcast experiments, we move to the projection experiments, and the projection experiments is separated for two parts. One is the process-oriented experiments, and then the downscaled experiments. So the process-oriented experiments aims to distinguish and quantify the influence of the each factor of climate change on the ocean acidification. The factors include the increased temperature. Here we use the increased sea surface temperature and the increased atmospheric CO2 and the increased river discharge. The changed value is projected based on the observed changing rate in 2015 minus the value in 2018. So use the simulation of 2018 as the control case. Another forecast is designed to test the contribution of each factor of the climate change to ocean acidification. The case one is only considered the influence of the warming. The case two is considered only the influence of the increased atmospheric CO2. And the case three considered both the warming and increased atmospheric CO2. And case four only considered the increased river discharge. And then for the downscaled experiments, the main difference between our work and previous work is that we did a regional WRF with the resolution of 3 kilometers to do the projection of the meteorology forcing based on the bias-corrected climate global model. So next, I will introduce our main finding. Before that, we first validate the NECAN with all the observations in this region. First, I show the performance of the nutrients in the 1D experiments in Mass Bay in different regions. So the red line is for the observation, the black line is for the model results. We found that in the deep side, the 1D NECAN could capture the seasonal availability of the nutrients, but it fails in the shallow side because in this side, it is located inside the Boston Harbor, where it is influenced by the multi-river runoff. So because in our 1D experiments, all the horizontal advection is ignored. So it means the advection is very important in the coastal region, especially in the estuary region. Without the nutrient supply from the river runoff, the model could not produce the observed variability of nutrients or other variables. But for the deep side, the NECAN did not only presents the seasonal availability of nutrients, but also captures the seasonal availability of the carbonate system. For example, the PCO2 and pH, the model results matched well with the observations. Next, we move to the 3D experiment to see if the simulation in the shallow region, especially the river region, can be better with the consideration of the 3D advection. And these two figures shows the comparison of the nutrients DO, calorifier, and pH in the outer Mass Bay and the Boston Harbor. So compared with the 1D simulation result, the 3D NECAN captures the seasonal variability of biogeochemical variables in the estuary region after a 3D advection of river runoff was considered. Then we move to the larger domain, the Northeast US region. Before we compare the biogeochemical results, we first do the validation of the physical part, because this model result is not validated in the previous work. So we focus on the temperature, salinity, and current. The temperature and salinity is compared with all the observations shown in this figure, and the results shown annual root mean square error of 1.4 for temperature and less than 1 for salinity. And for the current, we choose the 3 kinds of observations in different regions: the ADCP in the New England Shelf, and the buoy observation in the Gulf of Maine, and the high frequency radar observation in the Mid-Atlantic Bight. And this figure shows an example compared with the ADCP observation. And NECAN captured the slope current and also the Wang ring. So NECAN could simulate the Wang ring well in this region. And compared with the buoy observation, the results show that NECAN could simulate the basin scale current inside the government region. And for the high frequency radar, this figure shows the measure and certainty of the high frequency radar. We found the error is increased with the distance from the coast, especially for the current direction. It can be as high as 80 degrees. We can't directly compare the model result to the HF radar observation, but we can compare in the region with lower uncertainty. For example, this figure shows the subtitle vorticity velocity comparison in the location of the right dot. And from this, we can see the model result match well with the observation with a root mean square and then 10 centimeter per second. So let's move to the comparison of the biogeochemical result. This figure shows an example of the comparison of nutrients DO carry file in Mass Bay region. The NECAN still captured the seasonal variability, even we expanded our computation domain to the whole Northeast US region. And for the oceanification related variables such as DIC, TA, and omega, we compare the anomaly from our result to the climatology data, and we found our model results mainly followed the availability of the climatology data. And we also evaluate our model performance by the model scale assessment based on the cost function, percentage bias, and adjusted relative mean absolute error. And from the performance score, we found the NECAN performance is at least reasonable for all the oceanification related variables. Next, I will introduce our main findings. First, we analyzed the processes contributing to omega in different regions. And so omega is influenced by the temperature, salinity, DIC, and TA. The sensitivity of omega to each variable is estimated by the variation of each variable when other 3 variables kept their annual mean value. For example, in the outer Mass Bay and the Georges Bank, the Mid-Atlantic Bight, the variation of omega is mainly followed the variation of DIC, but in the region, for example, the Boston Harbor, Scotland Shelf, and Gulf of Maine, where the variability of TA is influenced by the river or the influence from upstream, the TA is also a dominant contribution to the variation of omega. So we also analyzed the process contributing to change in TA and DIC. And TA and TIC is both influenced by the net community production, the NCP, the calcium calcification and dissolution, and also the remineralization from the benthic, and also the physical transport. But the difference is the TA is also influenced by the denitrification and nitrification, but the DIC is influenced by the LC interaction. And this figure shows the changing trait of all the terms in the equations. Use the mass bay region as an example. We found in the outer mass bay, the change of TA is mainly dominated by nitrification and denitrification, NCP and advection. The change of DIC is mainly controlled by the NCP and advection. But in the Boston Harbor region, the advection, the contribution advection is increased, especially for the TA. The TA variation is mainly followed the advection. So the normalized TA and DIC relative to constant salinity is commonly used to examine the mechanism of the biogeochemical processes contributing to change in TA and DIC, and the stoichiometric ratio in change of TA and DIC is summarized by the previous work. And one thing need to be pointed out is that the sulfate reduction is not included in NECAN. And this figure shows the normalized, simulated and observed TA and DIC, and the black dot is for the simulation result, and the green dot is for the observation. For example, in Mass Bay, in the Boston Harbor, the simulated normalized TA and DIC, the slope of them is about 1, but considered that there is no sulfate reduction in NECAN, this slope is more close to the nitrification and denitrification. This indicates that in Boston Harbor, the nitrification and denitrification process is the primary driver for the biogeochemical TA availability. And in the outer Mass Bay, the change in we can see the scatter can be concluded as 2 slopes. One is near the slope of NCP and LC interaction. Another is near the nitrification and denitrification. This indicates that in this region, the biogeochemical change in TA and DIC are mainly controlled by the multiple processes. Similar in the Northeast US region, in the Gulf of Maine and Mid-Atlantic Bight, the biogeochemical TA availability is controlled by the nitrification and the denitrification. But in Scotland Shelf and Georges Bank, the change in TA and DIC is influenced by the multiple processes. And the Wang-Rin and Wang-Rin eddies can significantly influence the water transport from the slope to the shelf region. We analyzed the Wang-Rin and Wang-Rin eddies during January to April in these 2 years to see how the contribution of Wang-Rin and Wang-Rin eddies to DIC flux from the slope region to the shelf region. So this figure shows the trajectory of the Wang-Rins. There are 5 to 6 Wang-Rins and about 10 Wang-Rin eddies in these 2 years. And the influenced duration of this Wang-Rin and Wang-Rin eddies is different with regions. The duration is longer in the Scotland Shelf and Northeast Channel, but shorter in Georges Bank and Mid-Atlantic Bight. And the DIC flux can be increased by about 35% with Wang-Rin and Wang-Rin eddies. And in Georges Bank, the water transport can be revised from the slope region to the bank when Wang-Rin and Wang-Rin eddy happened. And next is the impact of the climate change to ocean acidification. But first, the climate change can change the circulation. This figure shows the velocity difference between the warming case and the control case. It's shown that the circulation over the Georges Bank is increased by 8%, and the circulation in Wilson Basin is increased by 48%, but the circulation in Wilson Basin is reduced by 40%, and the inflow from the northeast channel is reduced by 50% due to warming, and this inflow reduced may be one reason of the weaken of the Jordan Basin circulation. But why is the circulation changed in Georges Bank? The Georges Bank, Georges Bank, the anticlonic shear is mainly a topographically controlled residual circulation with its intensity multiplied by nonlinear interaction between the stratified tidal currents and the bioclinic density gradient. So we found the cross isobar density gradient is increased under the warming condition. So the enhanced stratification is a primary driver for flow intensification over Georges Bank. But for Wilson Basin and Jordan Basin, this is a different story. In these two basins, the flow is mainly controlled by the density-driven bioclinic flow. So we compare the velocity difference and the geostrophic velocity difference. We found the difference pattern is consistent between these two. This means the bioclinic geostrophic flow, the change in the bioclinic geostrophic flow is the reason why the circulation over in Georges Basin and Jordan Basin changed. And we also analyzed the minimum omega of different cases, and also the months when minimum omega occurred and the layer where minimum omega occurred to see if the climate change will influence this. And we found as the current condition, the March is the highest probability month with maximum area of the minimum omega over the northeast shell. And the minimum omega is more likely to occur at surface in Scotland Shelf and Gulf of Maine, but at bottom in Georges Bank and Mid-Atlantic Bight. And the warming will increase the probability of having the minimum omega to occur earlier and at the bottom, especially in Gulf of Maine region. And the increased carbon dioxide loading will increase the probability of having the minimum omega to occur at the surface, because the interaction from the ocean and atmosphere is mainly happened on the upper layers layer. And the influence of river is relatively small compared with other factors because the influence is mainly limited in the estuary region. And we also analyzed the vertically averaged omega difference to see the contribution of climate change as a regional scale. And we found the warming will increase the omega by about 6%, but the increased atmospheric CO2 will decrease the omega by about 8%. But consider these two factors, the contribution of the increased atmospheric CO2 will mostly cancelled by the contribution of the warming and leading to a change about 2% in vertically averaged omega. And we found the change in DIC plays a primary role in the omega-A variation, and the decrease of DIC and the warming condition is caused by the enhanced NCP and reduced air-sea interaction. But both NCP and the CO2 air-sea interaction will be enhanced due to the increased atmospheric CO2 loading. However, the DIC increase caused by the enhanced air-sea interaction is bigger than the decrease caused by the enhanced NCP. So it leads to an increase of the DIC in the in the atmospheric CO2 increased case. But the contribution of the climate change on TA is limited within 10 micromole per kilometer. It is much smaller compared to the impact on DIC. And in the downscaled experiments, we found the similar circulation change in the downscaled experiments. But besides that, because we do a downscaled meteorology field, we found the storm may be stronger and in 2015, especially in the late summer and fall. And with the consideration of the storms, the stratification in our region may also be changed. And in spring and summer, the stratification is enhanced, especially in the Wilson Basin because of the warming. But during fall, the stratification is decreased because of the enhanced mixing due to the more storms in our region. And we also the ocean acidification stress can be estimated by the duration and intensity of exposure of organism to the lower omega condition under 1.5. And we found at the surface, the exposure duration in Georges Bank and Mid-Atlantic Bight will be 2 more months in 2015. But in Scotland Shelf and Gulf of Maine, it will be similar as the current condition. But at the bottom, the exposure duration will be year-round in most regions of Gulf of Maine and Scotland Shelf and the slope regions. And for the intensity, we found the bottom Gulf Stream, especially the Wilson Basin, will be the region under the most ocean acidification stress. But compared to the Gulf of Maine water, the Georges Bank may be one of the regions under minor acidification stress in 2050. But how the climate change, if the climate change will influence the the biogeochemical process on the change in TA and DIC, we found only the contribution of NCP and LC interaction will be enhanced in Scotland Shelf, Gulf of Maine, and Mid-Atlantic Bight. But for the Georges Bank, the NCP and LC interaction may be the main driver of the biogeochemical variability of TA and DIC. And here is our summary. We first developed and validated NECAN and examined the physical and biogeochemical process contributed to ocean acidification. And we also estimate the impact of climate change on ocean acidification condition in 2050. And we found omega is mainly controlled by DIC in the Mid-Atlantic Bight and Georges Bank, while by DIC and TA in the Gulf of Maine and the Scotland Shelf. And TA and DIC are primarily impacted by the physical transport in the estuary region, and the biogeochemical variability on DIC and TA is mainly controlled by nitrification in the Gulf of Maine and Mid-Atlantic Bight, but by multiple biogeochemical processes in Scotland Shelf and Georges Bank. The Wang and Wang added will enhance the DIC flux from slope to shelf by 35%, and warming will intensify the circulation over Georges Bank and in Wilson Basin, but weaken the circulation in Jordan Basin. And warming and increased atmospheric CO2 loading play opposite roles in the omega change. Their contribution on ocean acidification will be mostly cancelled by each other on the regional scale. Meanwhile, the ocean acidification stress at bottom will be enhanced. The biogeochemical driving mechanism for the change in TA and DIC will remain unchanged, only with the improving contribution of LC exchange and NCP in Scotland Shelf, the Gulf of Maine, and the Mid-Atlantic Bight. But the LC CO2 exchange and NCP will become the primary driver in Georges Bank. Okay, thank you. Okay. I can take any questions.
Yeah, I want to add something, it's like when Lou do thesis, Bob Beasley and Jill give the greater support, but Bob's lose his memory, so he's not able to talk in the public anymore. So that's the reason I just want to, make appreciation to the Bob and the Jill's help. Okay.
Great. Thank you very much, Lou. Are we going to hold questions like we have been till the end of the three, or did we want to start?
Yeah, I think we should. Well, we can take questions at the end of the three presentations, but if you have questions for Lou now, feel free to put them right in the chat and we can circle back to them during the Q&A session.
Great.
So next up we have Kate Liberti. Kate is a research associate and PhD candidate in Damian Brady's lab at the University of Maine. Her research has focused on understanding the relationship between physical and biological drivers of carbonate chemistry in Maine estuaries and modeling the impact of oyster growth in aquaculture settings on estuarine carbonate chemistry. She's been involved with OA in Maine since 2016, starting with the Maine Ocean and Coastal Acidification Partnership and continuing with NECAN. Go ahead, Kate. You should be able to share your screen now.
Okay. All right, thank you. Thanks for inviting us to talk here. So today I want to talk about some similar topics to what Lou was talking about, but just moving inshore and looking at estuaries. So what do we need to know to model ocean acidification in estuaries? And I would say probably the most important thing is to first just, and this sounds obvious, but identify what the point of your modeling is. I think we can look at the big scale and get really good projections for what it's going to look like in the future. And in the near shore, we have to really understand what our point is and if there's a direct application. So are we looking at modeling pH because we want to know what the change in pH is going to have for different organisms, or are we looking more at omega? And answering that question before we really get going will help drive what we're focusing on. Hold on one second. So estuaries are the meeting place of rivers and the ocean. They're very complex areas and they have very rapid change. A lot of the rivers that come in have low total alkalinity, low pH, high CO2, and oftentimes high organic matter or inorganic nutrient loads, which can stimulate phytoplankton blooms, and all of these changing conditions will impact carbonate chemistry. So just like Lou was mentioning, it's the combination of the physical and biology and biogeochemical cycles that are going to impact carbonate chemistry. And oftentimes when we're thinking about carbonate chemistry in estuaries, three big themes are discussed, which are temperature changes, especially in temperate areas where we have large seasonal changes in temperature, salinity and the impact from low alkalinity freshwater, and metabolism. And when we talk about modeling ocean acidification, this brings in some new challenges. So today I'm going to focus on two big things. One is what parameters are being modeled. As I mentioned before, if we're modeling pH and we can measure pH, that's great. If we're modeling omega, then we need to be able to calculate omega, and the choice of what parameters you use to calculate omega can impact your results. So we're going to look at that, what the errors associated with that are. And especially in Northern Gulf of Maine, we don't have a ton of data to validate these models. So looking at what are the gaps, just kind of the entire point of this NECAN series is where are our gaps in monitoring, what should we focus on, and what should we prioritize for the monitoring so that we can validate models that are built. And then making sure that the data is of good quality. And then second, we're going to move into looking at two different estuaries, the Damariscotta River and Casco Bay, and looking at how the relationships between the physical and biogeochemical drivers impact carbonate chemistry in these two very different estuaries, and what the implications for modeling are. So on the west left side here, we have Casco Bay. Portland is in the bottom left corner, and Friends of Casco Bay has maintained 3 long-term monitoring stations, and they use a YSI sonde that collects temperature, salinity, pH, and DO, as well as chlorophyll and turbidity. And then they use a Turner PCO2 sensor to get a time series of PCO2. And then in the upper right corner, we have the Damariscotta River. Back in 2018, we had a buoy in the upper river, and I did some carbonate chemistry discrete sampling. And so we are going to be using that to calculate omega in the Damariscotta. And the reason I want to focus on these two estuaries is that they're just very different from each other, both in terms of shape, in terms of freshwater inputs, and just what's coming in from the watershed. And so they provide a really good contrast to each other to see how omega responds to different drivers in these different areas. And then first, I used two different methods to calculate aragonite saturation state in Casco Bay. So I used the in situ pH and PCO2 from Friends of Casco Bay. And then secondly, I used the same pH, and I calculated omega using total alkalinity, which was derived from the salinity total alkalinity relationship with the shell day data, specifically from Casco Bay. So the relationship between salinity and total alkalinity for at least this one day in Casco Bay was this. It was a pretty good relationship. And I used this real-time salinity data, or not real-time, but the monitored salinity data from the SON to calculate total alkalinity using this, and then that to calculate omega. And the next figure I'm going to show has 4 plots. They're all of omega, and 3 are going to be the sites in Casco Bay, and 1 will be Damariscotta. And you'll see the 2 different lines of omega calculated with PCO2 and then TA. So the first thing that just jumps out is that PCO2 is in blue, and it's much lower than what is being calculated with the total alkalinity in orange on the top. For the Damariscotta, we didn't have PCO2 data, so it is just pH and TA. And so this was kind of a conundrum, because it gets to that question of, we say you can calculate omega with any 2 of the 4 parameters. But when we think about modeling and what input data we're going to use, we really need to consider what makes the most sense, and not only from a errors in terms of measuring and fouling, but also just, there's best practices in terms of like which methods of measuring parameters and combining them have the most amount of errors and whatnot. And sometimes when you add in all of the internal errors and then the fouling errors, you can get pretty big differences between omega calculated in different ways. In this case, the PCO2 sensor has some issues with drift and no anti-fouling measures. And so although this data is corrected as best possible, I think that's still playing heavily into the results that we see here. And so this, the data you're seeing now is still a bit of a work in process. It's my last research chapter with my dissertation. And so we're going to be exploring this difference a little bit more and bringing in some more data from Casco Bay to look at it and make sure that we're confident in the data that we're calculating. But this was kind of just something I wanted to highlight, and that is really important as we start to move into modeling and deciding monitoring priorities, that we think about what the best, a combination of sensors that can get high resolution data and discrete samples that can get DIC or TA, which is going to be a lot more stable in order to calculate omega going forward. So on the bottom right of this plot, we have the upper Damariscotta omega calculated in 2018. And at first, I'm going to go through and kind of highlight the drivers that are changing omega in that system, and then we'll switch back to the drivers that are changing omega in Casco Bay, and then do a comparison. So one of the things I did with the Damariscotta data was to use a regression tree and look at splits in the data that are associated with different aragonite saturation states. This can help us identify when, at what points different parameters are important. So we have data from the end of May through the beginning of October, and it's a temperate system, so you're going to expect a pretty good temperature range in that time period. I believe it went from about 12 to 24 over this time period. And so the first thing that jumps out, the first 3 splits are all physical drivers, which we would expect because that's a pretty big temperature range. So we have temperature as number 1, and then temperature and salinity as our second and third splits. And then after that, we start to move into more of the biogeochemical parameters, whether it's chlorophyll or turbidity. Turbidity can be limiting primary production with light shading, or it can be increasing nitrification with the resuspension of particles. And so if you look at the bottom part of this figure, we have the time series of omega, and it's highlighted with the different splits. So if you look at the red at the beginning and the end of the season, that is when we had low temperature, which is going to lead to low aragonite, and low chlorophyll. And when during that time period, if the chlorophyll is a little bit warmer, but a little bit higher, but we still have low temperature, then the aragonite is bumped up a little bit. That's shown in black, kind of towards the beginning of the season. And then as we move more towards the middle of the season, our temperatures become moderate, and then turbidity becomes important. So whenever turbidity is a little bit lower, under 3.6, we have higher aragonite, and when it's higher, we have lower aragonite. And that holds true throughout the middle of the season. So even when the temperature is high and the salinity is high and stable, whenever turbidity is low, the aragonite is higher. And then we have one big kind of increase in aragonite towards the beginning of September, and that is when we have the highest temperature, the highest salinity, and the biogeochemical factors, at least here, are not popping out as being important, but we'll touch back on that in a little bit. So to kind of look at these processes in a time series way, I've plotted the left is tidal amplitude, so it's just meters above mean low or low water, and that's in the gray in the background. And what I want to highlight is that there's one large spring tide a month during this time period. And the current speed, which is the top plot here in black, is really sensitive to those large spring tides. We go from about 2.5 meter amplitude up to 3.5 meter amplitude. And the current speed really jumps up. And in response, the turbidity also increases during these spring tides. And so in part, you have a possible impact on metabolism, just for, as I mentioned, with the turbidity increasing from light shading and lower primary production, and also perhaps more remineralization of organic matter or nitrification with the resuspension. But in addition to that, in the third plot, you have nitrate. And what you can see is after each large spring tide, there's a little bump in nitrate coming into the system from the Gulf of Maine. So we kind of get this advection of offshore water into the river with the higher amount of water that's just coming in. And that does end up stimulating the chlorophyll a little bit. In the fourth plot, you can see, a few days after the bump in nitrate, you get a bump in chlorophyll. That doesn't really tell the whole story, because as you can see in the bottom plot with omega, during a time when omega is really increasing a lot in mid to late August, the chlorophyll is actually decreasing. There's small bumps, but overall it's decreasing. So we wanted to figure out, what is going on at this point. And so the last plot I'm going to show you for the Damascata is looking at net ecosystem metabolism, which Lou touched on being really important. And at least in this plot, this is normalized aragonite, so it was normalized with a constant temperature and salinity. And what I've highlighted in the boxes are times when net ecosystem metabolism was positive. And you'll see during those times, we often see increases in omega, especially that late August instance. We had 2.5 weeks of sustained autotrophy, which is a little bit unusual, and the omega really increased during this time. So we know that at least in the Damascata, the physical drivers are important over a seasonal scale. The biological drivers, the net ecosystem metabolism, is really important on shorter scales, and they're very coupled to tidal cycles because of the shape of this estuary. It allows kind of an incubation at the top. And so any influx from the Gulf of Maine, whether it's nutrients or outside chlorophyll, is important in terms of determining omega in this system. So to shift a little bit to Casco Bay, I'm going to compare Casco to the Damascata a bit. And so this is just a temperature and salinity plot. I have the Casco Bay sites on the left for 2021, top temperature and bottom salinity. And then just a quick comparison between Cousins Island and the Damariscotta on the right for 2018. So you can just see that in general, Casco Bay is a colder place and it has higher variability in salinity in general. The 3 sites are influenced by 3 rivers that flow into Casco Bay. And although the Damariscotta is called a river, it has very low freshwater flow with pretty stable salinity. So this is going to really be driving some of that variability in the aragonite in Casco Bay is more frequent salinity decreases and just more variability in the temperature and salinity in general. Looking at the metabolism between the 2 sites, between the 2 estuaries, 3 sites in Casco Bay. The Casco Bay sites have a smaller metabolic range than the upper Damariscotta. And they start highest kind of in the late June, early July, and then taper off into November, which makes sense. You're losing daylight each day at this point, and so you're having a lower metabolic range. But interestingly, in the upper Damariscotta, we have a sustained high metabolism period between July and September. So it looks just shape-wise a bit different from Casco Bay. And just to look at it in a little bit different way, the metabolism in Casco Bay is a box plot here. And so Cousins Island is on the left, Portland Harbor, and then Harpswell. And Cousins Island in the middle of Casco Bay is net autotrophic all season. Portland Harbor, conversely, is net heterotrophic every month except June. And then Harpswell starts off autotrophic and then decreases to heterotrophic. And I'm going to show again the aragonite saturation state. And the aragonite in the system follows that same trend in terms of Cousins Island aragonite is mostly the highest, with the exception of Harpswell's few peaks, and relatively stable with the net autotrophy all year long. Portland Harbor is the lowest and relatively stable. And then Harpswell starts out high and then towards the end of the year decreases towards low. And so we can see that metabolism is also important in Casco Bay, but it doesn't necessarily follow the same strong relationship to tidal cycles as it does in the Damariscotta. I'm working on using some generalized additive models to look at these relationships a little bit more and really figure out what is driving these changes in aragonite in Casco Bay. So more to come on that in the next few months. So how does this all relate to modeling in estuarine environments? I think what we need to keep in mind is that each estuary can have really different relationships between these processes, due mostly to the shape of the estuary. Is it long and skinny and it incubates water, or it's more open to Gulf of Maine water? How much freshwater flow is there? How much influence is there from the Gulf of Maine? And then the overall residence time. We found that residence time is just so important for many different factors, whether it's increasing temperature through solar radiation, or it's incubating nutrients and allowing for really quick remineralization. It's just a really important parameter that needs to be included in physical models that are going to feed into biological models. I shouldn't say included, but taken into account. And so biogeochemical models that include these features and fluxes are going to best resolve all of the processes that change carbonate chemistry. And then once we have a good handle on that, we'll be able to do future projections that can look at how those biological and physical processes are projected to change in the future and what the results will be for OA. I'm going to hand it over to Damian at this point to talk a little bit more about those models.
Yeah, so I am I'm going to get a little bit up on my soapbox because it's been interesting to me, I guess, to see as we've evolved and tried to start to model acidification. And Lou did a fantastic job, I thought, and really underscoring how many different variables you have to take into account just to get the shelf and slope acidification dynamics correctly. And ironically, it can even sometimes be more difficult as we get closer to shore. You know, it's easier to sample, but there are a lot of other things going on, and you know, chief among them, I think, is biofouling, and trusting our continuous monitoring over time is really really challenging. So I like bringing up the plot on the right. Everyone's probably familiar with this. This is Alec Wang's paper, you know, looking at some of the original TA to DIC ratios and aragonite saturations up the coast from Texas and Louisiana, with relatively high total alkalinity to DIC ratios, and you know, in less than 100 meters, aragonite saturations that are well above 3, to the New Hampshire transect, right, where the aragonite saturations already hang out at 1.5. And I think Kate just showed a lot of data from our Maine estuaries demonstrating that our aragonites are consistently above and below 1.5, and driven often by net ecosystem metabolism, where we are net autotrophic for periods of time, and that bumps us up above 1.5, and then we end up going heterotrophic, and we end up below there, right? And so a lot of the past history, I think, of estuarine acidification modeling has really come out of the Chesapeake, because it's a place that had a lot of existing infrastructure and management level models. But a lot of where we need estuarine models happens to be way up here, where I'm sitting right now. So if you go to the next slide, Kate. Many of you will be familiar. I was lucky enough to chair the Science and Technical Advisory Committee for the next generation of the Chesapeake Bay model. If you're not familiar with that model, you know, this is what I mean by existing traditional water quality or biogeochemical modeling infrastructure, where you have essentially land use, land change models, airshed models, pollution control, land use models, precipitation, meteorology. Lou did a fantastic job, because in many ways she recreated some of those aspects of a traditional water quality model for the Gulf of Maine region, Georges Bank, outer Massachusetts Bay. That gets connected to, in our Chesapeake case, for instance, a phase 6 watershed model, and then into an estuary model where you get predictions and total maximum daily loads, and you compare that to water quality standards, and then you go back to the data model inputs and generate scenarios to try to ameliorate the water quality changes that you saw on the front side. And so a lot of fantastic work has been done in this realm, but there really is not a water quality model used in management north of Massachusetts Bay. And so a lot of the infrastructure that's necessary in the area of the country right now that is potentially very susceptible to acidification, you know, does not exist right now. If you go to the next slide. So I think we correctly developed estuarine acidification models in areas with lots of water quality infrastructure. And so this is a figure from the Coastal Hypoxia Research Program days, from Jeremy's paper, using RCA in this case, but it's a good spaghetti and meatballs diagram that shows what these traditional water quality models calculate over time, and they are of course focused on dissolved oxygen. So the next plot, Kate, then is essentially the same model. This is in fact, you know, Jeremy's update to adding to the traditional water quality model and adding the carbonate system. And in many ways, URSM, what Lou showed before, encapsulates most of the processes here, right? So we took everything that you saw on the previous diagram to the left to model dissolved oxygen, and we tacked on dissolved inorganic carbon, calcium carbonate, total alkalinity, atmospheric CO2, as well as carbon dynamics associated with sediments and sediment flux models. But we have yet to bring that to the fore and bring it up here. So now we sort of have to come out of that street light where the light was previously and go out into the dark and figure out where we lost our keys, because, you know, here we have 543 sub-estuaries. Most of them are producing shellfish, whether it's 65% of the nation's soft shell clams, or the burgeoning oyster industry, scallop aquaculture, you know, lobster, if we want to go all the way. But I think we're going to have to try to understand some of these nearshore distributed estuarine systems in the northern Gulf of Maine. And I think Lou's model has been a fantastic eye-opening for me, because I think now we have the right boundary conditions to use in some of these nearshore models like Casco Bay or like the Demerskata in places that are large shellfish growing areas. So that's my soapbox, right, is that we need to start connecting the models that Lou showed earlier for boundary conditions and start generating sort of management style level models for northern New England estuaries if we're going to really understand these dynamics, because the period of time that we spend underneath 1.5 on the aragonite saturation scale seems to be directly related in some ways to how heterotrophic these estuaries are and what they're processing over time. I will get off my soapbox and hand it to Sam.
Thanks, Damian, and thanks, Kate. So finally, we'll be hearing from Sam Siedlecki. So in addition to being the co-chair of the NECAN Steering Committee, and she's also on the NECAN Science Working Group, she is an assistant professor of marine resources at the University of Connecticut. And as an oceanographer, she focuses on coastal regions where she implements numerical simulations to investigate and identify processes within that environment responsible for the biogeochemical dynamics in both the modern and future oceans. She received her PhD from the University of Chicago, where she focused largely on theoretical systems of the ocean. As a postdoctoral fellow at the University of Washington, she began simulating Washington and Oregon waters using realistic simulations of ocean acidification variables and hypoxia developed as part of the coastal modeling group there, and extended that work to include seasonal and short-term forecasts. As an assistant professor at the University of Connecticut, she's begun exploring regional climate projections of ocean conditions on both the west and east coast of the US. And through work with colleagues on both coasts, she and her group at UConn are partnering with social scientists to bring relevant tools into decision-making frameworks to aid coastal communities and the challenges they face with respect to marine resource planning. Take it away, Sam. You're on mute, Sam, but we can see your presentation.
Okay, great.
There you go.
Perfect. Well, thank you so much. I'm taking a little bit different tack. I'm not going to show a ton of results from the models that we have I'm going to instead focus on, based on that work, what I think that the observational needs are for to support this kind of modeling that's talked about. I agree with a lot of the results that have been shown, and there's a lot of impressive work in the prior two presentations. So I just wanted to start off with a couple of things, like what like some bullets around like what modeling, how modeling could use observations. So one, we've seen this through the couple of the talks earlier today, is through model evaluation. So this is really important, not just for saying that you can understand that what the model results mean, but from a scientific perspective for use of scientific investigation, but also in terms of as we try to bring these tools into use for management and risk assessments and vulnerability assessments, that evaluation is critical to build trust with the communities. This is important on the forecasting timescale as well as on the regional climate downscaling projection timescales. It's also important for scaling up of these impacts. And so as we start to bring the effects of ocean acidification into and using scales of different types of models accumulated together to get to upper trophic levels and impacts to fisheries, it's important that we also consider evaluation there and sort of think about kind of how we can evaluate the impacts that we're projecting and forecasting in the natural environment. And then finally, there's a lot to say on how observations could be used to help reduce uncertainty in various ways for projections and simulations. And I'm going to focus on one aspect there, which is the parameterization of important processes that are really currently poorly resolved or not resolved at all in some cases. And that's very important for attribution studies, like some of the work that we saw here presented here today. This is from, I forgot to put my own citation there, but it's from our 2021 paper that shows a map of like where the current observations are in the region. There's various degrees of how often they are observed, but there's not very many real-time observations that are available within the region. And so this is important because as you're developing forecast and projection space tools and trying to bring those into this kind of decision-making space, it's difficult to do that without this kind of real-time evaluation available. And I often say that this is like if the forecast says that it's going to rain and you go outside and you experience that it's raining, then you sort of start to look at that forecast more and develop a relationship with it. That we all do that now without really thinking much about it. But in the ocean, there's no way to do that without this kind of real-time access. And so and correct me if I'm wrong during discussion, or put links into the chat, but as far as I know, there's not very many of these. There's on this map, we have the CML and the BUID. And BUID is the only one that's available on the NERACUS website via real time, and sometimes that's not the case. That's the challenge of real time observations, right? But there's and there are some in Long Island Sound as well. But in terms of OA variables, I think that's pretty much it. There used to be one on the OOI mooring, but now that array has been moved, and so that's no longer in the Northeast region. It's been moved further south. So that is something that we could say is a priority for this kind of moving forward. So those assets can be used in order to make these kind of climatological comparisons. And so we did that with 2 regional simulations for the region. One of them is a ROMS model that we work with here at UConn, and the other one is from the Canadian group and led by Deanne Lavoie. And so you can see the long-term climatological comparison of surface saturation state here, the present values in the boxes observed, and then and so this kind of evaluation is, with all the statistics and whatnot, is something that helps to build trust that the model does what it's doing for the right reasons. Okay, and so, but the other way is also with the stakeholders, and so stakeholders tend to rely on certain observations in order to make decisions. And as I've been moving to work more closely with the scallop fishery on our regional vulnerability assessment project, one of the things that we've leaned into is to kind of do comparisons with our models with observations made by the fleet directly. And so this kind of comparison with the simulations is also one that helps to build trust in the tool. And so we are limited because of what we are able to offer the fleet, right? And so this is a project that's joint between Commercial Fisheries Research Foundation, so CFRF, and WHOI. Glenn Gorkowitz has been leading this and was kind enough to share the data with us in order to help us to achieve this trust building exercise. And so what we did is compared CTD observations that are limited to physical observations currently of temperature and salinity, but there was recently a workshop at OCB, and there's an interest, in the fishing community to expand this to biogeochemical variables, of which OA could be one of, right? In addition, there's also these empirical relationships that could be used to extend these basic hydrographic information into carbon variables. And that could also be another approach for some of these long-term observational assets where we might have there's more oxygen observations out there, for example, and so we could use some of those. And so that's an approach that we do in order to try and extend some of these observations historically as we're doing these long-term historical reconstructions. So this is something that one of my grad students, Hong Nguyen, who's pictured there, I forgot to put his name there, but he's doing comparisons between some long-term historical observations of oxygen from the Gulf of Maine and the simulations that we're working with, which include both a regional ROMS model and regional MOM6 jointly with GFDL. And so we're kind of looking at these long-term trends in order to try and assess how well the simulation is doing over multiple decades. Assessing and attributing the variability to various processes. One of the challenges that he's finding, so there is his name in the list of collaborators finally, in that trend analysis and observational analysis, this is all from World Ocean Database for oxygen. You can see that there's a map there in the lower left-hand corner, and those are not color contours. They're actually individual dots of oxygen observations that are available within each of those subregions. But of course, those observations vary in time. And so what you're looking at here is the percentage of the casts that come from the various regions over the time series that he's been analyzing. And you can see that, the relative contribution between the different shelf areas changes over time and is not consistently stable, right? And so kind of consistent observations over long periods of time of these variables is really important to kind of on this long-term trend time, scale assessment. So, moving then to sort of scaling up, I just want to say a couple of things here. One, another student that works with me, her name is Hallie Berger. She's been working on a dynamic energy budget model for scallops as part of that regional vulnerability assessment that I was talking about. And so here she is inputting food and temperature and carbon dioxide from the simulations and then running a model that is parameterized based off of some lab-based observations from Chen and Masek's lab that are described in Poos et al. In 2023, and then investigating the controls like a sensitivity experiment on the various drivers to understand what role they might be playing. And she's finding, we're looking to understand sort of size and sort of how long it takes for scallops to get to harvest size and how that might be impacted by these multiple stressors going forward. And so here are just some results showing shell length variability from over time. This is preliminary, this is a work in progress, but suggests that there's an interaction here between warming, ocean acidification, and food within the region. And so how, if we were to project that the sizes of these, scallops were, were changing over time, should we evaluate that kind of going forward, in these long-term simulations? And, can we develop some observational ways of evaluating these kinds of model predictions for the fishery, which is also something that we're working on. And so then the last bit is to kind of talk about reducing uncertainty for these projections and thinking about unparameterized processes that we might need to get further observations in order to better understand. And of course, we all know that the Gulf of Maine in particular is experiencing this trend that's opposite to the global surface pattern for saturation state, where that Joe has nicely quantified in this paper showing the increase in saturation state, and that has been discussed in the prior presentations. And of course, and Joe broke that down, into kind of what was using a simulation, in combination with observations to break down kind of how relative role of various processes were to that. And here, what I want to stress is that other effects are a combination of sea surface temperature, salinity, and total alkalinity. And there's a table in the paper that kind of breaks those out and sort of, and the conclusion is that it's the water mass advection that's driving this this modification and the dampening of the OA signal from fossil fuel emissions, which is consistent with the modeling results, right, that we just saw. But there's also been some results that were recently published from observations from Barney Balch's recent paper that it's all pixelated because it's a very small picture that I zoomed in on from his paper. So if you want to see it better, I suggest going and checking it out. It's a very dense volume. There's a lot of information in there, but this is salinity normalized total alkalinity, which also, was observed to have a statistically significant, trend and increase in the region over this time period. So there's a lot of different processes that can modify or global that are happening in the coastal. And we've heard a lot about those, through the previous talks. And one of those in particular is this benthic interaction and these biogeochemical fluxes, that are happening between that sediment water interface. Again, something that Lou showed really nicely that, that the denitrification can impact the overlying water column. And so there aren't very many observations. Ooh, let me just turn off the volume there. There aren't very many observations of this. And so during the last OCA cruise, we went out and my colleague, Professor Craig Tobias, and our co-advised master's student, Alex Frenzel, we went out and took some cores as part of the OCA cruise. This is showing a GoPro video that we strapped to the multi-core here, showing the on George's Bank, where we were able to collect some cores and get some incubations going in order to get some better resolution on these sedimentary processes going on over the region. And so you can actually see, I don't know if the resolution will be good enough on the streaming, but there's some critters moving around there in the video on the bottom of the benthos, because there was lots of organisms there as well. So there's just not very many observations. This is a figure that we made showing what we wanted to propose to do. The white, so what you're looking at here are percent calcium carbonate of the surface sediments from the USGS. And then the proposed locations, although we didn't make it to all of those, I'll show you where we ended up in a second. And then the triangles represent where we have observations currently before we went out and took these samples of sediment fluxes. So there's just not very many in the region, and most of them are near shore. And so we were able to collect cores from those locations there in red. We tried the ones that were also empty, but those were unsuccessful. And so have those coming online to sort of think about. This is important because there's been some work on the global scale showing that calcium carbonate cycling is something that could be an important feedback in the future. So this is from a paper from Sulpus et al. From 2018 that really highlights the importance in the North Atlantic of anthropogenically derived dissolution of calcium carbonate at the benthos. There's also been some work on the global scale showing the changes expected from coccolithophore growth, and in the acidified ocean and responses to that, which if you look at the regions in the North Atlantic, there's supposed to be an increase. And this is because they parameterize coccolithophore growth as a function of temperature, CO2, nutrients, and light. And they're thought coccolithophores to be carbon limited. And so as the CO2 increases, they actually, increase. And whether or not that should be the case in our area is something to think about, especially given some of the importance that's been shown to the variability of light and nutrients from those prior presentations as well. Globally, there's a paper that just came out talking about the total alkalinity simulation capacity from CMIP5 versus CMIP6, and you can see that the alkalinity bias was reduced between CMIP5 and CMIP6 here in the surface oceans, but that in the subsurface, they still don't do very well, and that there really is no consensus on how to simulate this calcium carbonate cycling. So there's some of them have peak production, some of them don't. There seemed to be most consensus over the river discharge in the global simulations. I'm not sure if that's true for us regionally. Now that there's multiple models that are available to think about sort of thinking about that, and sort of no consensus on what happens with the PIC once it reaches the seafloor. PIC is particulate inorganic carbon, and so again, Barney has some observations in his recent paper talking about trends in some of these important phytoplankton classes within the Gulf of Maine, and he's suggesting that there's a shift from there's overall a decline in primary production, and there's a shift in the kind of primary producers, from diatom assemblage to more of a dinoflagellate dominated one, but also has some patterns in coccolithophores that are relevant to this conversation as well, that are talked about within that. So I'll just end there with my recommendations that, we increase our regional capacity for real-time ocean acidification variables to be available to help with the development of these tools, that we think about as a community, the biological impact observational approaches, which I look forward to the next webinar series coming up, I think even next week on this topic. I didn't talk about this because we had another session about observational estimates of anthropogenic carbon, but those are really important because as we're going to be seeing, I'm working on one, and I'm not sure if others are as well, but sort of the anthropogenic carbon content maps from these simulations would be well evaluated with an observational based estimates as well. And then there's some particular parameterizations of important processes that are important, that could feed back on total alkalinity in particular, that would require some additional observations around these sediment fluxes, as well as calcium carbonate cycling within the water column, in particular rates around that process locally, I think would be really important. With that, I will stop and start us off with some questions, which it looks like there are some in the chat. Dwight, you had a question for Lou at the beginning, so I guess I would invite all of the speakers to return your video back on if you could, and join us for kind of a panel discussion. I know that we only have about 5 minutes or so left because everybody, there will be a recording, and I want to be respectful of people's time. We can stay a little bit longer, but if people need to leave, know that you can put your question in the chat and we'll try and answer it within a few minutes late, and you can watch the recorded answer of it later, or if there isn't time, then we can just respond via email to some of the questions that emerge. So Dwight, I know you had a question for Lou. I wanted you to be able to ask it, so why don't you?
Sure, I'll try to be quick. Yeah, so fantastic work, really impressed by the modeling work you're doing, and I was wondering, from the validation exercises you were engaged in, did you encounter gaps in observing data that you felt would have helped that validation exercise? And I note that you really illustrated the importance of NCP and denitrification. And should we, as we think about augmenting our observing measures, should we make a concerted effort to make explicit direct measurement of those rate processes?
Yes, I think so. Because for now, my validation is mainly focused on the nutrients concentration, the current file, and the DO, pH, PCO2, this part. I didn't do any validation about the NCP rate or other rate. If we have those observations, we can do a better job in the model parameterization. Yeah, we could have a better performance in our model. Okay.
Can I follow up on that question, Lou?
Yeah, right.
The sulfate reduction process wasn't included in the biogeochemical component of the model, right?
No.
Do you think if it was, this is asking you to speculate a lot, but do you think that if it was, it would change your findings as far as denitrification versus sulfate reduction?
I'm not sure for that, because the paper I read is found that in the S3 region, I think it's your paper, right? In
Maybe.
the S3, yeah, it's the nitrification and denitrification is the primary driver. But I think if we could include the sulfate reduction in the model, it will explain more details about that. Yeah.
Oh, can I ask one more quick follow-up? How hard would that be to incorporate? I'm not a modeler, so I don't know how much effort that would require to include that process.
I'm not sure because I didn't know how the sulfate reduction works,
Sure.
and I didn't know the processes of this. But if I think it's It's not so difficult if we know the equations and experimental parameters of it. It can be included in the model.
You know, so I can add something about this. So we compare the UGRCA, the model was the mass bay and the NECAN, but UGRCA had a much more complicated structure than the NECAN. Okay, we compare with the DO. So we find, you know, okay, no, even the NECAN has not in the completely, you know, no dynamics of process like a UGRCA, but the DO simulation is exactly the same. That means you have a different, you get a same answer, but like a different reason.
Yeah.
So that's why, you know, most of the biological model, I think is a, no, like I think a sense and, you know, the parameter, you know, parameterization is very critical. You know, what do you want to do the parameterization, how to do that, so they can change it. Okay. So then I feel that if you have data, you know, most important, we have observation data, we can make a more validation in the model, see what is the parameters is important now. So that's why, that's the reason, so when we discuss the issue, should we add that? So later we feel like, you know, because we don't have enough data, we cannot prove that's really true or not. We better keep the way we have. Right.
So were you able to do any comparisons to some of the regional data that's inside, in particular Mass Bay, the sediment fluxes, and how did your simulation perform?
You know, so when we do the UGRC, you know, the Massachusetts Bay, so we do find, you know, the sediment data not have a lot, you know, good coverage. You know, some places they have, some don't have. That's why we had to treat the sediment flux very simply way. So because it's very hard to compare, They do have some data. You know, we run it for 1995 to 2006, but then we found that compare sediment is really difficult.
Yeah, it wouldn't be the same time match, right? Like
different time match, different thing, you know.
But was it even in the same ballpark? You know what I mean? Like in terms of that.
Yeah, that's why.
And that's where we're at with this, right? There's so few observations. I agree that it's like, is it even
that's why I like what you mentioned. You know, do the sediment measurements. That's really important.
Yeah.
You know, because you know, like Lou was mentioning for climate changes, he found, you know, in the Midland by the other region, the bottom will be very sensitive. No, the oceans, because of stratification, the warming could water stratify. Lot of no OA, you know, it's kind of, you know, like omega value go down, but near the bottom. Right, because that's the way, you know, what you said is, no sediment management is really critical. If you, everything's shifted bottom right now, right? That's why, you know, I think it's that's the reason we see the NECAN, we choose the NECAN, we didn't choose the other model, because we said the NECAN had a basic, you know, they had a sediment module. So they had a whole loop, just like Damian said as a loop, right? They had a water column, they had a sediment. It's really important. Like we had people use like an MPCD model in the region, but they only have a water column.
Yeah.
They don't have a basic process, right? So that's why the CHP model, they found the basic is very critical. The reason we think that's, you know, NECAN probably can do the better job. You know, mostly problem we have right now, mostly come from river, because we don't have a flood information for TA, for DIC. You know, because you have a driver model, you have the boundary condition, you know. So then the river boundary condition is really issue for us. Now we use the temperature, we use salinity data, get a TA something, but as the variability is so larger, right? The bit near estuary region, because salinity change a lot. Okay, sometimes be 0, sometimes be 5 to 4. That's why really hard with salinity data to predicting the TA data was river.
So I also want to point out, Damian put, thank you, in the chat, a link to there's an OCB group that's forming about a work group. Damian, did you want to say more about that?
No, I was going to ask, by the way, on the sulfate reduction and the denitrification, which we have a lot of experience with, but usually when we have hundreds of sediment flux measurements, right, in a place like the Chesapeake, we're doing one for Delaware right now. We have 300 measurements, right? I can't imagine there are 300 measurements anywhere in Maine, let's say, and that's 3,500 miles of the tidal shoreline we've been talking about. So I put in the chat there an OCB group called Benthic Ecosystem and Carbon Synthesis, where we are going to be sort of trying to get as many measurements on the Northeast Shelf as we can sort of put together and do seminars to talk a little bit more about carbon cycling in the sediment and benthic ecosystem sort of writ large. But I think if sulfate reduction and denitrification are as big an impact as Lou, you're demonstrating here, assuming most of the denitrification is happening in sediments, then I think, getting these databases together for validation, and particularly if you haven't been able to validate the denitrification rates you have so far, is going to be super important.
Thank you for that.
I think it's I like what the case was analysis for the data from the Cascade Bay region. So we are developing a very high resolution model in the region right now. It's 10-meter resolution. So we was nesting for the NECAN. That region include the wetland, include the watershed region. That's why after the model developed, we really like to working with the University of Maine group to see how we can use the model to validate the data there. So this one, I think Kate did a very nice analysis.
Thank you. Yeah, that model sounds great. I'm really excited to see it.
Yeah, and I guess the other question I had for you all was about the model that you showed, Lou, was about your open ocean kind of boundary conditions, sort of how the carbon changed in particular, and maybe oxygen as well, like over the long simulation that you did.
You mean for the projection experiment?
No, I meant the historical, but the projection was another question that I had.
Okay. So for the handcast case, we use the all the available observation we collected and near the boundary to do the boundary condition. Mainly is for example, we deal it with different region. For example, for the Gulf region, Gulf Stream region, and also for the northern boundary region, they are different. And the other things is vertically because in the Gulf Stream region, for example, for the nutrients, the Gulf Stream, the nutrients is concentration is very low in the Gulf Stream region, but in other region, the nutrients concentration is higher in the deep layer. So we treat it differently. And for TA, it can be calculated from salinity with our physical model, but for DIC, yeah, we mainly use the climatology data to do the boundary condition. And yeah, in the projection experiments, we collected the data from the 3 global climate model, and we calculated their trend in the US Northeast region, and we added this trend to our 2018 condition to do the projection experiment.
Yeah, so the DIC, forcing being a climatology will just mean that anthropogenic trend in the open ocean won't be present, right?
Yeah.
So that's been one thing that we've been thinking a lot about in terms of how to bring that in, because that open ocean boundary, like as Joe's analysis showed that water masses are changing. And there was another webinar about the anthropogenic carbon that, there were some interesting talks there about that and sort of what the water masses changing might be bringing in. And I think that's also a real challenge in the modeling community, to sort of how develop, processes on how to do this to couple with the global simulations. Not what we're talking about here in terms of observations, but like something, since we're all together, just sort of think about and talk about kind of as we move forward.
One thing about boundary condition, most critical boundary we found is the Nova Scotia shelf, Scotland shelf. So that's we found, like climate, the global model did not get a, kind of simulation correctly, but it's really very tough. So recently we have studied for satellite data. We use like satellite SNE data, UK have data, the update 2022. So we found that salinity coverage, the data, for satellite data in the Nova Scotia pretty good compared with the observation. So that's why Lou has been rerunning the model right now for his 2017, 2018, also 2050 projection. Use the satellite due to the data simulation, satellite data, SAT data into the system. But then we use the projection to 2050. So what happened? So we run the model. So before we publish the paper, we want to include that part. And make sure we get a Nova Scotia Shelton transport corrected. So I compare the model you use for Wang for other climate change model.
Yeah.
So I think it's it's hard to compare because it's a boundary condition issue, right?
Yeah.
Yeah. So that's the reason we say want to do some study for this. Yeah. So we try to improve the model, then get a good model for people everybody can use.
Yeah, I always think it's good to have an ensemble too, like of different
ensemble,
approaches all saying the same thing, or pointing out where stuff is.
I always think it's an interesting thing that we run your runs model with our projection immunology forcing, because before the immunology forcing use a global model, but then we compare with 6 climate change model for the region. None one was get corrected for temperature change. That's why we selected the NCAR, the sense model, because they has a capability. They use real analysis data, they capture temperature. Even for this one, Lou didn't mention today, but then we still found that the SAT, train is not corrected in our region. So then Lou was doing another correction. So uses kind of, global, climate change model driving a 3 kilometer regional wall. We had a climate change wall 3 kilometers, then you get a whole mesoscale structure immunology corrected. Not correctly, just a result, right? We don't know correct or not because of climate change prediction. So this way, then you drive an ocean model, then you can both downscaling for immunology and the ocean. So we already had a 2050, WRF down for 3 kilometer resolution. So the Damian and I talking about, here lobster project. So we will provide a physical field to him. He will do the lobster training, tracking. Yeah. So something we need to have both downscaling for atmosphere and ocean model.
Yeah. Modeling needs.
Yeah.
Definitely.
Yeah.
Great. Okay. So there is a question from Beth to Kate in the chat as well, but I want to be cognizant of the time. Maybe that could be the last one, and then we can wrap things up. Kate, did you want to?
Yeah, sure.
Did you want to ask your question?
Yeah. Beth asked, are there any examples of data that, oh, sorry, I misheard you. Beth, would you like to say it?
Yeah, sorry.
Sure. Kate, I really enjoyed your talk. This is great work. So we kind of go along assuming that 1.5 is the right idea of whether there are going to be impacts. And that's mostly from experimental, lab studies. So are there any data in nature, especially in the Damascata, where there's been co-located data taken with species information as well as biogeochemical information that we can actually use to think about organisms in nature versus in the lab?
Yeah, I was actually having a conversation with Chris earlier about this in terms of whether we, really want to kind of use 1.5 as something as a sharp threshold, I guess. You're right. In experiments, it's been shown to be kind of the point where you start to see detriments. And I put it on the graph just as a reference point. But personally, I don't think out in the environment, you're going to be able to do studies and attribute any negative effects you're seeing directly to omega or pH. I think, moreover, we should be thinking of omega as, the lower it is, the higher the level of chronic stress on an organism, and the more energy and metabolism they're going to have to use to overcome that. So we were discussing many shellfish can regulate their internal pH and be able to biocalcify even at low omegas, but that might take more resources. They might need to eat more in order to do that. And one of the analogies I had thought of is there was a study on people in terms of like, what was the impact on their metabolism when they were forced to live in low temperature environments, not out in the open, but if they kept their house temperature at 50 degrees, it doesn't sound like something that's going to kill them, right? It's not a hypothermic situation. It's just a chronic stress. And what is the impact on their metabolism and all the other kind of like stressors, their cortisol levels when they're forced to live in that? And I think that's a better analogy for omega. It's just that if other resources are scarce and other conditions are poor, this might push them over the edge if it's low, but it's not something until it gets very low that's going to like become like a canary in the coal mine of like, oh no, everything's going to die. And Chris brought up, you know, shellfish in the Northeast have been living through fresh, cold springs for eons and been fine, right? They're used to the variability. It's just when we think about modeling this, it needs to be like, what is the future omega going to look like? And also, what are the other conditions going to look like? Is food going to increase? Maybe it won't be that big of a deal, but if food's also decreasing, then we get to a point where we might see it. And none of this takes into consideration predation, which is a huge issue for a lot of wild shellfish populations. So it's, I didn't answer your first question. I'm not aware off the top of my head of specific studies that have tried to match carbonate chemistry with organisms and attribute that, but my gut feeling is just that that would be really difficult because of the kind of the whole setup of it.
All right, well, thanks everybody for this great webinar. I don't know if Emily, you wanted to advertise the next ones and sort of sign us off. The questions in the chat, if there are still ones that are remaining, which I think there are, if folks wouldn't mind sort of emailing the people that asked them in response, that would be awesome. Yeah.
Thanks, Sam. Yeah, I just wanted to thank everybody again. Thanks, Kate and Damian, Lou and Chen, and thank you, Sam, for your presentations. Our next two webinars are next week, next Monday and Wednesday. The information is up on our website, so go check that out. But also it's going to be going out in our mailing list as well. So hopefully everybody here is signed up for that. So once again, thank you, everybody. Thanks for staying over so we can continue our discussions. Those are always great. And we'll see everybody next week.